So I can't express how truly delighted I am to be here in person and to congratulate Joe, whose work has truly made a difference from my life in physics. And I'll say a few more words in tribute of Okay, and I'm also, of course, very grateful to Eva and Don for organizing this amazing meeting. It's hard to imagine a gathering like this and to ask me to speak at this meeting. Okay, so I'll be talking about actually a series of papers that somehow appeared since the summer in collaboration with Simone Giombi, and who is an assistant professor in Princeton, and Ben Safdie, and then a recent paper with Arkady Tseitlin, and now we're working with Lynn Fay and Simone on a new paper. This is Okay, so but before I plunge into this higher spin stuff, I just wanted to reminisce a bit. So I wanted to reminisce a bit about those amazing times in 95, 96, etc. And without an exaggeration, many people from my generation remember that day when Joe's paper appeared. And one thing I remember is that Ed Witten was giving a series of talks about string duality in Princeton. And then, just for those who didn't fully appreciate Joe's paper, the next morning he said, I was planning to talk about X, Y, Z, but Joe Polchinski just threw in a monkey wrench into my plans. And the joke at T was that people kept repeating is, finally we have the brains we could think with, because before they were these a bit hard to grasp objects. So I think, so you can still see Joe's red hair in this picture. Okay. And a couple of lines from that paper, well, besides the string duality, obviously it was important that D-branes are the RR-charged, Ramon-Ramon-charged objects. But here is a line, presumably one should think of them as an alternative representation of the black p-branes. And that's really the germ of the idea that at least influenced many of us very much. So it's actually not far from there to gauge gravity duality, because once you start saying that when you stack many branes, you have a macroscopic amount of charge, and then there is this classical solution for in particular for the three-brane, which is non-singular, obtained by Horowitz and Strominger. And so we have two ways to think about this object. One is a lot of D-branes on top of each other, and the other one is this curved space. So, and that's basically, in a nutshell, gauge gravity duality. Then one can explore this at low energies, for example, throw in objects from far away and see how they tunnel into the small R region, or study the near extremal entropy. And I'm actually happy to see my collaborators from those days, Amanda Pete and Arkady Tseitlin here. So we ran into this three-quarters problem, which in those days actually scared quite a few people from working, in particular on the three-branes. But then it turned out that it wasn't a contradiction. It was really a prediction about strong coupling behavior. And then, of course, Juan came in with his amazing observation that at low energies, you really are zooming in on the AdS 5 crosses 5 throat, and it teaches you something about strongly coupled gauge theory. And whenever I think about those days of stacking branes, somehow what comes to mind is this scene from the movie Rain Man. Probably many of you have seen this movie, where Dustin Hoffman's character is this idiot savant. And there is this memorable scene where he's in a bar in Las Vegas after a big win, and suddenly this rather forward young lady approaches him because she overheard about his big win, And then she starts sensing something weird about him, and she says, so what do you guys actually do here? And then and Dustin Hoffman says, we're counting cards. We're counting cards. And what else do you do? We're counting cards. So I think a good answer for some of us was, we're stacking brains. We're stacking. And what else do you do? We're counting states. So this was definitely the era from, and then, so of course, after the ADS CFT came along and all the limits were spelled out, it's been a preoccupation ever since. And many insights about strongly coupled gauge theory come from weakly curved metrics. You know, you can learn about all sorts of facts about strongly coupled CFTs, even confining theories. But actually, non-BPS tests of the duality are still quite few. They mainly come from high-powered techniques like integrability and supersymmetric localization. But there are actually not that many tests, and still a proof of the duality remains elusive. So the question is, could this be because actually both n=4 super Young mills and type 2B string on ADS 5 crosses 5, they're both really complicated theories. So, we're pretty sure that they're dual to each other, but to study each one and the limit it doesn't like is not easy, right? So the question is, can we learn something about simplified models of ADS CFT? And if you basically ask people what CFT can you name, say before the recent period, n=4 super Young mills would probably not be something that comes to mind. The first answer would be just a free theory, right? Just the theory of a free conformally coupled scalar. So the question is, can one do something using those more familiar CFTs? Or, for example, the Wilson-Fisher ON models. So what Polyakov and I proposed in 2002 is to essentially study these souped-up versions of these free theories. But you have to make them large n. So the idea is you, instead of just one scalar, you take n free scalars and just restrict to the ON or UN singlet sector. And that's actually the theory that we will claim we have a dual description for. And then one can also study interacting theories, like where you add a relevant operator, like phi squared operator. So one can flow from this free theory to this interacting ON Wilson-Fisher point, for example, in 3 dimensions. So in these cases, actually, supersymmetry doesn't seem to help much at all. But what is important is that there are conserved currents of higher spin. And they're all singlets, namely this color index is contracted. So basically, in a nutshell, instead of the adjoint matrix field and by n matrix fields, you just have n vector fields. And those are, in some sense, more familiar theories which have lots of physical applications and so on. So now one can, so I mentioned that in the theory of n real scalars, you only have even spins. But the most important even spin is 2, right? So these are supposed to be some versions of theories of quantum gravity. But one can also consider theories of, say, n complex scalars. And then in that case, you have currents of all integer spin. And there is also a scalar field whose mass squared, basically whose dimension is just d minus 2. It's just twice the free dimension. Now the dual, so if you think about ADS CFT, in ADS CFT we always have, whenever there is a conserved current, there is supposed to be a gauge field. There is supposed to be a gauge field which has gauge invariance, which is dual to this conserved current. So the spectrum of the dual theory has to contain these gauge fields of all spins, and the scalar field in the bulk whose mass squared is adjusted to reproduce this, the dimension. And then amazingly enough, so when you think about it, and you look up papers by Vasiliev and collaborators, they actually have theories with exactly this spectrum. And they were led to study theories in ADS and DS space, not because they wanted to, but because they had to, because these theories are really not consistent in flat space. And the big leap in this field was when Frodkin and Vasiliev had this proposal to put the theory in ADS space. So it was sort of an ADS theory waiting for its field theory dual, and the field theory dual seems to be this. So, but certainly it's not a simple theory in ADS space. Although I would venture say that it's still a lot simpler than string theory, because it roughly speaking has only one Regge trajectory. And these equations of motion that Vasiliev wrote down are a little bit like a baby version of string field theory. They're not that well understood because there is no known action principle. So there are still some really important missing tools in this game, but they can be used. Okay, so what is the evidence for this duality? Well, we can consider, for example, the matching of the spectra I already discussed, but one can consider, kind of formalize it in a nice way by considering the theory on SD minus 1 cross S1, the field theory. This was done by Schenker and Yin in 3 dimensions, and in a very recent paper, Giombi, Zeitlin, and I generalized it to arbitrary dimension. The interesting thing is that this free duality doesn't seem to have any critical dimension. It seems to live perfectly happily in any dimension. And actually, to derive these formula, you just have to do something similar to what Juan did, namely integrate over this holonomy field. And after you integrate over it, you find that in the field theory, the singlet partition function is just a square of this free scalar partition function. Just free scalar one-particle partition function. And these formula actually were written down by Fleita and Fronsdal, essentially. They didn't know about large N and UN singlets, but they just knew about products of characters of the conformal group. So the mathematics was essentially already there in the Fleita-Fronsdal papers, and they called this a product of 2 singletons. And then they were expanding the product of 2 singletons in terms of characters of all spins. And there is this remarkable identity. Well, you basically decompose it in all spins, and you check that sum over all spins is indeed equal to this. The other nice feature is that this character for each spin is exactly what the computation for higher spin in ADS gives. So this is a kind of nice check of just the spectrum agreement. But you could say that this is, in some sense, part of this game. If this failed, then none of this would have made any sense. A more dynamical test is matching of 3-point functions. In fact, Giombi and Yin kind of revived this field a few years ago by actually using Vasiliev equations to compute 3-point functions and show that they agree with free field theory. Now, just the fact that the free theory is free doesn't mean that the bilinears decouple, right? So in fact, there are non-trivial correlation endpoint functions for the current bilinears, and they agree at the 3-point level. And one interesting thing you find is that the inverse of the Newton constant is exactly n, but I'll come back to this. I mean, the quantization of this was derived by Maldacena and Zhubayadov, and this is also a very important ingredient in this duality, just the counting of interaction. So at large n, you again get a weakly interacting theory in ADS space, just like you get it for the dual of n equal 4 super-Yang-Mills. But now let's do something a bit more sophisticated, a little bit closer to how we do anomaly matching in ADS CFT, right? We compare, say, one of the big news in ADS CFT was the computation of anomaly by Henningsen and Skenderis, and how it matches, it can be obtained from the bulk. Now, we can So one can, for example, consider Euclidean AdS, whose boundary is now not SD minus 1 cross S1, but just SD, just a Euclidean d-dimensional sphere. And you want to compare the bulk calculation of the partition function with the field theory calculation of the free energy on the sphere. So here the frustrating thing is because we don't know Vasiliev action, we cannot compute the leading classical term of order n. But what we discovered is with Giombi is that it's actually very instructive to compute the one-loop correction, because you actually know that the fluctuations of these higher spin fields are just free fluctuation fields. And for them, everything can be done. In fact, everything was done years ago by Camparesi and Higuchi. They obtained concrete results for all the heat kernels and one-loop vacuum energies. And what we decided to do is just to sum them up over spin, sum them over the entire spectrum. And this actually is a very sensitive test of this conjecture, as it turns out. Because when you think about in the free CFT, the result should be just n times the free scalar answer. For example, in d equals 3, it's n times a certain number that you can extract from the three-sphere determinant. And there is no correction of order 1, no correction of order 1 over n. It's just exact. But then, so if you naively you would say that only this term should be non-zero, the classical term, and the one-loop term should just cancel when you sum over the spectrum of the theory. And actually, this is what happens for the theory of all spins. And it takes some work to check it in 3 dimensions. So in the process of checking it, we also realize that there is a bulk UV divergence that actually cancels when you sum over the spectrum. So it establishes the bulk finiteness of this Vasiliev theory. If you throw away one spin, I don't know, spin 17, you will not obtain the 0.
So this is not a Bose-Fermi cancellation?
No, not at all. You have to do some kind of proper regularization. What comes in is that the sum of squares of all even integers is 0, like zeta of minus. I was reading this New York Times article.
I guess the point is that it's logarithmic divergence, right?
Yeah. It's
the power law divergence, which is the sum of the energy.
right. Yeah, so one has to construct some kind of analytic continuation procedure. Like, so in that video, they were holding Joe's book, right? Ed Copeland, and they opened it, and they saw 1 plus 2 plus 3 plus 4, etc. equals minus 1/12.
I want to correct something here. If you look carefully at the video, it's not an equal sign, it's an arrow.
Okay. Right. It's actually on that. We're working on that level. Actually, we can justify it. If you read our papers, I mean, I cannot flash all the formula that we had there, but there is something called the spectral zeta function, which has a spectral parameter. It turns out that this parameter regulates both the sum over modes of each field and the sum over all spins. And then one can just analytically continue in the spectral parameter and get the sort of the answer. So these are the kind of, but here you can just see that using the usual zeta function regulator and using that zeta of minus even number is 0, you prove the one-loop finiteness of the spectrum. One has to work harder. It's not enough just to know about Riemann. You have to know about Hurwitz and Lerch to regulate the sum, to regulate the finite part. And you, for the theory of complex scalars corresponding to all integer spins, you do get 0. But then, and this is something we completely didn't expect. It was a minor epiphany for us. When you sum only over even spectrum, which corresponds to ON rather than UN, we completely, without wanting it, stumbled that the sum is equal to this magic number log 2 over 4 minus 3 zeta of 3 over 8 pi squared. I mean, it's not a number that you can get by accident. It's this now. We just stumbled that you regulate it, you analytically continue, you get this number. So sum over all even spins equals one scalar. The question is why? Actually, you get this number divided by 2. You get equal real scalar. And here is what we believe happens. So this is this should be an arrow, sorry. So you get exactly the F value of a real massless scalar field. And this can be all explained by just a shift in the identification of the quantized coupling from n to n minus 1. This shift actually is a pretty standard thing for ON models. It's essentially related to O1 being trivial. And this shift is exactly what would be allowed by quantization that Juan and Zhubayadov told us. So for what we can't do yet is evaluate the classical term and show that it's equal to n minus 1 times. So we're basically saying that 1 over g Newton is not n, it's n minus 1. And then there is a one-loop shift that compensates it. It's a bit like an anomaly or one-loop shift in Chern-Simons theory. And that's basically what has to happen. And then so if you don't believe this, we actually wrote 2 more papers to build our own confidence. Because it's not only in 3 dimensions, it happens in every single dimension. So for every dimension D, 2, 3, 4, 5, etc., sum over all spins in AdS-D, all even spins in AdS-D plus 1, and you get the number, which is that for one real scalar. It's an amazing thing. So for example, for even dimensions, like for D equal 4, it's just the A anomaly matching, it turns out. So then there is a logarithmic divergence in the AdS-D plus 1 volume, which means that you're really computing this A anomaly. And we know what's the A anomaly for a real scalar in 4 dimensions. It's just 1/90th. And you get it by this zeta function summation. I'll show you in a second. There it works really simply. You don't need Hurwitz-Lerch zeta function. And then when you go to 6 dimensions, you get minus 1 over 756. Just always works. So let me show you what is involved in 4 dimensions. You get these sums. And then just do completely brute force regularization with zeta function. You get zeta minus 3 and zeta minus 5. So it cancels in this case. And in this case, it gives you exactly 1/90th. So, and the same thing we played in all higher dimensions. So it looks like this, it's all explained by this one loop shift from n to n minus 1. Okay, and then more recently we saw that exactly the same thing happens for Casimir energies. Casimir energies are related to anomalies, but they're not exactly proportional to A anomaly because there is also this derivative anomaly, D-type anomaly. So there's some independent set of numbers. And again, we saw that just by summing over Casimir energies in AdS over even spins, you actually get exactly the Casimir energy of one real scalar field. And another comment is that for any sensible CFT in 3 dimensions, the Casimir energy must vanish because there is no anomaly. If you take an AdS4, a theory with a gauge field, 3 scalars, and something like this, it's not going to vanish. It's not consistent with just theorems of so it's just a slight criticism on bottom-up model building. but for this, so you really need all the spins for these cases, and then it vanishes. So in odd dimensions for all sensible CFTs, it really must vanish, and here it vanishes due to summation over spins. Okay, so just doing free CFTs is a little bit boring, of course. So what can we say about interacting CFTs? And here is another thing that Joe wrote some really nice papers about double trace flows, the importance of double trace coupling. So here the interactions are of double trace type. And we know part of the AdS CFT dictionary is that for a certain mass range that Brighton, Lohner, and Friedman pointed out years ago, there are really two allowed values of dimension, delta minus and delta plus. And you can, so the Vasiliev dual in AdS4, there are two different allowed boundary conditions. The delta minus equal 1 gives you the free theory, delta minus equal 2 gives you this interacting theory, and you correctly flow from one to the other by turning on this double trace operator phi squared squared. And then one can even compute this f quantity minus logarithm of z on the 3-sphere, and you see that it decreases consistent with the f theorem. The f theorem just basically says that f in the UV must be bigger than f in the IR. Okay, so this is all basically was already said years ago, but now let me talk about something a bit more fun, which is, it's also part of it is known long ago, but let's think about the Gross-Neveu CFT in 3 dimensions. In this case, you add psi bar psi squared interaction, but that's irrelevant, right? So in that case, there is evidence that there is a UV fixed point. But UV fixed, for example, whenever I give talks, people complain to me about UV fixed points. I mean, at large n, you can just do the usual Hubbard-Stratonovich trick, but it's still, you want to build a little bit more confidence about UV fixed points. So, and then we realized that actually this UV fixed point already in the early 90s was explained as a result of flow from another theory in the right direction. Namely, one can start in 4 minus epsilon dimensions, for example, with just the Yukawa theory and flow to the IR and obtain exactly the same theory as this in 4 minus epsilon dimensions. And this is the work by Zingerstein and Marché and Hasenfratz and collaborators. There is a very nice review by Marché and Zingerstein about this stuff. So, and this just says that this Gross-Neveu fixed point, at least for large n, is perfectly reliable. And you can see that from these beta, these are just Yukawa beta functions from well-known. And then you see that there is an IR stable fixed point of these beta function equations. And the interacting theory is basically, so there is a fermionic conjecture similar to the bosonic one that Polyakov and I made, that was made by Lee and Petko and Sezgin and Sundell. And there is a slightly different variant of Vasiliev theory in 4 dimensions, which appears to be dual to either free fermion model or the interacting Gross-Neveu model. But now, so let me just finish with since I've had, I do need some more RG, that's the title of the conference. Let's think about 5 dimensions. So in 5 dimensions, there is, one can also add an irrelevant phi squared squared interaction. And formally, there is still a UV fixed point. And one can say that this fixed point is dual to Vasiliev theory with just the other boundary conditions. But here is a question. Is this fixed point real, or is it just something not reliable? So, one somewhat peculiar thing about it is that it appears that negative values of the lambda phi to the 4 coupling. And then, but let us just think about whether there is some kind of UV completion of this theory. Namely, there is some other theory from which you can flow to this fixed point. And this is what we're now trying to write up this work. And it has some dangerously old-fashioned flavor to it, but as far as we can tell, no one has actually done this in the 70s. It's essentially take an ON symmetric scalar theory in 6 minus epsilon dimensions and consider large n. So there is essentially a unique ON symmetric theory. And again, one can just compute beta functions. And then there is an IR stable fixed point. So you basically flow from a free theory to this interacting theory in 6 minus epsilon. So there is this fixed point. And as far as we can tell, it's indeed identical at large n to the UV fixed point of the phi squared theory. So here is, so there is some interesting pattern of fixed points. And you can indeed flow from the free UV theory to the interacting IR theory. But something truly amazing happens for this theory. Large N expansion breaks down at 1040. Have you seen a large N theory which is we don't, basically these fixed points just disappear. They go off to the complex plane, so they become complex, and then the unitarity is violated because then the dimension of the field is no longer real. So they clearly become non-unitary, but so it's a very interesting exercise in one-loop field theory, which well, it's probably the 1000 has to do with 6 that you're in higher dimension, but we were stunned to see this. But yeah. But I mean, this is still rather special to being in 6 minus epsilon, right? Because you can't go too high in dimension. So, for example, the dimension of the sigma field in this theory, it's above unitarity bound if G's are real. But if G's are complex, then bad stuff happens. And we can see that the value we get from our G analysis agrees with the kind of large N bootstrap that Petko did long ago. And I should say that the idea to study this theory for N equals 0 goes back to Michael Fisher in '78. It's the well-known attempt to study Lie-Yang edge singularity starting with 6 minus epsilon. But just with N equals 0, it's certainly not a good theory. In particular, you can see that unitarity is violated right there. But for us, it's perfectly okay. So we seem to be perplexed by this, but it seems like just finding some nice new interacting theory in 5 dimensions seems a good justification, and having Vasiliev dual for it is another good thing. So now let me just end. So I hope I convinced you that higher spin AdS CFT is certainly about quantum gravity, because when we do one loop, we do one loop gravity in AdS and one loop higher spin, and some rather miraculous things happen when you add up over spins. And renormalization group methods are as important as ever, but there is a feeling that there is much room left for new tools to explore this duality. Maybe something like D-branes is what we're missing. So happy 60th birthday, Joe.
Thank you. Kind of an off-the-wall question, but there's this fascinating ABJ triality, which seems to really deepen the subject by connecting it to string theory, but it's been largely neglected. Do you see things that you can do with that, the calculations?
Yeah, that's an aspect that I just haven't had time to talk about. I haven't talked about this whole idea of what is it that makes these theories singlet. Like, for years I was worried about it myself. Like, is it okay to just postulate that you restrict to singlet sector? But then this great idea came, just couple it to Chern-Simons in 3 dimensions. Okay, then everything seems to become okay, and there is this very systematic way of coming back to singlet sector. Now, in terms of, so the ABJ triality is related to that idea, but it's also somehow is related to having Vasiliev fields themselves forming bound states, and that has not played a role in what we're doing so much. So far we have not connected this. This is in some sense simpler stuff. I mean, it's just trying to work this free field theory in the singlet sector. One comment that I can make is that there may be a way to couple this free field theory to a topological theory, and in this way enforce singlet constraint properly in higher dimensions too. But yeah, and we're thinking about that now. But yeah, I don't have connection with that.
Can you go back to this for? Yeah, this one. So you see you have n divided by 4 pi cube, right? 4 pi cube, it's 1000.
Yeah, it's not. Yeah, I don't think this has. Yeah, I don't believe that this is related to 4 pi cubed.
No, because n parameter is not n, but n divided by 1,000.
Yeah, I mean, it's a question of solving these equations. Yeah, you see the 4 pi, you can scale, I think, this 4 pi cube out of, you're just looking for zeros of these expressions.
No, but
and you can just scale it out.
no, it will come together with
Arkady will talk about it. Yeah, I mean, you can scale epsilon out and 4 pi cubed out. Yeah, multiply this by 4 pi cubed. It gets absorbed in epsilon, then the whole thing. Yeah, I think it's somehow just related to these coefficients. And it's a surprising thing. But I mean, to begin with, you worry, is this theory stable? You know, you start with this cubic field theory. But when you've flown to the fixed point, you're really in the infrared. So you, I think, strictly speaking, are only supposed to be just checking the spectrum of dimensions and coupling.
But this was an attempt to get this UV fixed point for negative coupling.
Right. There is this large N fixed point, which is really okay between 4 and 6 dimensions. Yeah, it does have negative coupling, but...
So the potential is unbounded.
Yeah, but I'm not sure.
And for large field strength, therefore, there are states with arbitrarily large energy.
Yeah, but the spectrum of it could be a problem, but the spectrum of operators appears to be perfectly unitary.
Can't you use the same argument to argue that for using the renormalization group for large states for which the field is arbitrarily big, you flow to the UV fixed point, which is arbitrarily negative.
At worst, we could be in some metastable.
Theory.
It's some kind of metastable, but maybe the tunneling is very suppressed in the infrared limit. But
Probably suppressed by N.
Yeah, it's certainly suppressed by N.
No. Assuming that the large N argument says that there's a fixed point with negative coupling. I mean,
right.
Doesn't matter.
Yeah,
It's unbounded.
you're probably right, but
That's like saying that the phi-4 theory in 4 dimensions for N goes to infinity is a sensible theory.
Well,
any finite N, it's nonsensical.
Yeah, the first thing you check, the question is, does it satisfy the axioms of unitary CFT? And I'm not sure it does. Yeah, it's not a ground state in this theory, but there could, well, I don't know.
Yeah.
In these theories, there is an instability that has an action which goes like e to the minus 1 over the coupling, and a coefficient which diverges has a UV divergence. So if you put the cutoff, then and you're recoupling, then this is, I mean, it's unstable, but it's non-perturbative in the coupling. So likely here you will get N in that action.
Yeah.
In the bulk, people have discussed this issue also, so you can have these ADS spaces which have instability control and one other paper.
Yes.
Horowitz discussed this.
No, that's fine. But I thought you were actually looking for a sensible theory with finite and
I'm not convinced.
Albeit big.
How about the following question? Suppose the bootstrap, there is now this vibrant bootstrap people. Suppose they look in 5 dimensions and find a solution of bootstrap equations that satisfies all the proper axioms. At least it makes me want to ask this question. Could this be actually okay? And I'm not completely sure it's not okay. But from the point of view of just RG, these beta function equations have a perturbatively okay fixed point only for n bigger than 1040. And this has nothing to do with non-perturbative instability.
Well, what about if you do it the other way around, starting from 4 plus epsilon?
Well, that is a less systematic way of doing it. I mean, if you have a UV complete theory and you just flow, that's why we embarked on all this. We just started flowing from above and.
Yeah, but if you have a UV complete theory with no ground state. Anyway.
There was some.
There were one. You had a question.
I already made it.
Igor in a minute.
There is some.
Just a quick question.
Just a second. You need to be recorded for posterity.
Security purposes. Is 1039 actually 1039 divided by epsilon, or
No. It's
not
1,000.
It's just a number.
No.
I haven't seen this number, but I have seen 365 in RG before.
I was brought up thinking that n equals 3 is large, but
Okay, so thanks a lot, Igor. And there's refreshments and coffee in the courtyard.
we started out thinking that obviously
And we reconvene at
not sensible.
11.